Assalamu alaikum. So today's topic is for class 12th subject physics. Topic is magnetic field due to a straight conductor carrying current. So if we have a straight conductor here, we have a straight conductor XY, and we have to find the magnetic field due to a straight conductor. It is carrying current. So here the direction of current is from X to Y. So in order to suppose P is the point where we want to find the magnetic field due to the straight conductor, and this point P is at a distance r but perpendicular distance from the current element. So at a distance a. So if we take a small element, current element IDL of a straight wire conductor at point O, suppose this is at a distance r from the point P. Let R be the position vector of point P with respect to the current element, and theta be the angle between the current element, this small element, and this R position vector. Let CO is CO thousand is barabar L. Then according to Biot-Savart's law, magnetic field at point P due to this small element will be equal to dB is equal to mu 0 by 4 pi IDL sine theta divided by R square. Now if phi is the angle at this point, then in this right angle triangle OCP, yeah, or POC, right angle triangle, this theta plus phi will be equal to 90 degree, because sum of three angles is equal to 180 and it is already 90, so sum of these two angles will be 90 degree. So theta plus phi is equal to 90 degree, that means theta is equal to 90 minus phi. Now here I have sine theta. Sine theta is equal to, then sine of theta is 90 minus phi, then is sine of 90 minus phi. We know sine of 90 minus phi is cos phi. Also in this right angle triangle I will find cos phi. So we know cos phi is equal to base by hypotenuse. So here base is this, a, hypotenuse is r. So base by a by r. So r is equal to a by cos phi. So r is equal to a by cos phi. And tan phi is equal to perpendicular by base. Perpendicular is this CO, that means L, and base is CP, that is A. So tan phi is equal to L by A. L is equal to tan phi. So I will differentiate this equation with respect to phi. So dl is equal to A is constant. So differentiation of tan phi is sec square phi d phi. So dl is equal to A sec square phi d phi. Now I will substitute the value of dl and r and sine theta in equation first. So instead of sine theta, I will substitute cos phi. So instead of dl, I will substitute a sec square phi d phi, and for r, I will substitute a cos phi. So after substitute, I will get this equation. So dB is equal to mu 0 by 4 pi I a sec square phi d phi divided by a square cos phi. So now dB is equal to mu 0 by 4 pi I a sec square phi d phi into, it will be cos square phi divided by a square into cos phi. We know sec square is the reciprocal of cos square phi, so cos square phi sec square phi will cancel, 1a will cancel. So here the equation will become dB is equal to mu 0 by 4 pi I by a cos phi d phi. This is the magnetic field at point P due to this small element dl. So to find the total magnetic field at point P, I will integrate this equation over the limit. So for example, I will over the limits from, I will write this angle theta 1, and here it is making an angle theta 2. So I will integrate the equation from theta 1 to theta 2 by taking the direction into consideration, then from minus theta 1 to theta 2. So I will integrate this equation minus theta 1 to theta 2 d by minus phi 1 to phi 2 mu 0 I by 4 pi a cos pi d phi. So integration, differentiation will cancel, it will come total magnetic field. So it will be, so these are constant, so they will come out from the integral. So it will be mu 0 I by 4 pi a minus phi 1 to phi 2 cos phi d phi. So now integration of sine phi is cos phi from limit is minus phi 1 to phi 2. So then b is equal to mu 0 I by 4 pi a. So first upper limit sine phi 2 minus sine phi 1. So, but we know sine of minus theta is minus sine theta. That will be minus minus will be plus. So, total magnetic field at point P due to this whole current element will be equal to B is equal to mu 0 I by 4 pi A sine phi 2 plus sine phi 1. Now, I will take some special cases. When the conductor xy is of infinite length, if the conductor is of infinite length and the point P lies near the center of the conductor, if this conductor is of infinite length and this point lies near the center of the conductor, then both angles phi 1 phi 2 will be equal to 90 degrees. So b is equal to mu 0 I by 4 pi a sine 90 plus sine 90. Sine 90 is 1 plus 1 is equal to 2, so it will be twice mu 0 I by 4 pi a. So that means magnetic field at for a long infinite length conductor, when the point is near the center of the conductor, will be 2 times mu 0 I by 4 pi. When the conductor xy is of infinite length but point P lies near and C. Now this point P is near, somewhere near this point Y. So at this, when it is near to Y, this phi 1 will be equal to 90 degree, phi 2 will be equal to 0. Then after substituting this, it will be mu 0 I by 4 pi A. This means, thus we know that magnetic field due to an infinite long near conductor, linear conductor carrying current near its center is twice that near one of its ends. That means magnetic field near its center will be twice than the magnetic field near one of its center. So direction of the magnetic field lines due to a straight conductor carrying current are in the form of concentric circles with the conductor as its center lying in a plane perpendicular to the straight conductor, and its direction can be found by right hand thumb rule or Maxwell's corkscrew rule. So according to this rule, if we imagine the linear wire conductor to be held in the grip of right hand, so that the thumb point is in the direction of current, so thumb point is in the direction of current, then the curvature of the fingers around, will represent the direction of the magnetic field lines, and tangent to these magnetic field lines will give direction of the magnetic field. And second is Maxwell's corkscrew rule. According to this rule, if we imagine a right hand screw placed along the current linear wire conductor, rotated such that screw moves in the direction of current, then the direction of the rotation of the thumb will give us the direction of the magnetic line is of force. This rule is, so I illustrated this rule. So today we find the magnetic field due to a straight conductor carrying current.